Alright, let's do the following and set up a spherical integral. So just abbreviation, yeah. Integral in spherical coordinates for the volume of the region bounded by x squared plus y squared is equal to 4, and also bounded by z equals 0, and one more equation, z is equal to root 9 minus x squared minus y squared. Okay, so let's just talk about this one. This is the top half of a sphere of radius 3. Yeah, the top half of a sphere of radius 3. Okay, so there's a lot going on, and this picture is going to be a little challenging to draw, but I think we should try. Yeah, so x-axis, y-axis, z-axis. Now, x squared plus y squared equals 4. That, just in the xy plane, is a circle of radius 2. Right? 1, 2, just a circle. But the point is, copies of that circle happen again for every possible value of z, not just z equals 0. So there's just copies of this circle on top and below, just stacked, right, above and below. So it's this tube, just this infinite, the tube that just keeps on going in the positive z direction, and even below the xy plane just keeps going below. It actually, while it does keep going below, we're going to have this lower bound of z equals 0 anyway. Then we also have this sphere of radius 3 that I'm going to attempt to draw in the picture here. So there's 3, 3. So we've got, well, let's try making that just a little bit rounder here. There. And then this continues back here, and maybe I won't draw all the rest of that part. So the key thing to talk about and to draw is you've got the top of the sphere here, yeah? And it's going to cut the cylinder somewhere and actually create, maybe I'll do this in a new color, it's going to create the shape of a circle right along here. And so there's going to be this top part, which would be like a little mound of ice cream, and it's actually going to be convenient for us because we're doing spherical coordinates to, let me try redrawing this whole thing actually. I just need a little more space. So let's do the let's draw down here a little more. Okay, x, y, z. Okay, so 1, 2, 1, 2, and so there's this cylinder that goes on infinitely, like that. But then at 3, there's a sphere, and yeah, this goes on, back here. It's like there's a circle in the xy plane, but more importantly, in the z direction, there's this popping like effect of this kind of thing, and it creates this circle here. That was a circle I was trying to draw in blue, I guess, a moment ago. But because we're doing spherical coordinates, it's actually going to be much nicer to think about. There's a cone here. So sorry with the negative y-axis getting in the way. But above this part, so there's this ice cream cone, really. And it's going to be much nicer to think about the ice cream cone on top. The ice cream cone. Okay, and then underneath, there was sort of what you can imagine like a cylinder. So this is the above part, okay? But then below, imagine that there was a cylinder, yeah, of radius 2. And so like this point is my attempt of drawing that point. And then there was let's just say a pencil, a sharp pencil whose diameter was exactly the same as the diameter of the cylinder, and it pushes into the Play-Doh and creates a dent into it. So it just cuts out part of the Play-Doh. Okay, that's the shape we're dealing with. It's actually going to help us out to just compute the coordinates of a point, like so that point right there. Here, y is equal to 0. So then at that point here, to get what's x and what's z, well, first of all, note that if we're on the cylinder, x squared plus y squared is equal to 4 still. So x squared is equal to 4, because if you plug in y is 0. X is plus or minus 2, but it's got to be x is 2 here, just based on the picture. We're on the positive side of the x-axis. And then we can actually, because the point we're looking at is also on the half sphere, we can just plug in to find the value of z, right? We can also get z is equal to root 9 minus, well, x squared, so 2 squared, minus y squared, or 0 squared. So this ends up being root 5. It means this point here, the coordinates of the point would be 2 for x, and then 0 for y, and then root 5 for z. And that's going to be helpful for us in just a moment. What I'd like to do is set up two separate integrals. Okay, the region that we have in this picture, splitting it up into two parts. There's a part that really looks like an ice cream cone, meaning it's like the cone is filled with ice cream and there's this mound of ice cream on top. Right, so I'd like to talk about that above part, which is the ice cream. That's the shape of it, ice cream that's sitting in an ice cream cone. And you'll notice for that part, it's so much like a sphere. So the rho values, you do have points that are close to the origin, and so you go rho goes from 0 to 3. What about the value of phi? So we're talking about, like, first of all, phi at the smallest can be 0. You've got points that are, in fact, close to the positive z-axis. But how far apart do you go? Well, that's based on the angle here. So we need to know what point. So there's this point right there. It also corresponds to a vector. Maybe I'll draw this vector in red. So from the origin to this point, there's a vector, and that vector would be 2, 0, root 5. Yeah, so we want to know that vector compared to this vector, what angle is created. Because whatever angle is created there at the, when the cone is at its widest, that's going to be the maximum possible value of phi. Well, fortunately, we have a dot product cosine angle formula that'll do this. So we just need to apply our old cosine angle formula to the dot product of the vector 2, 0, root 5, okay, for this vector in red. But against what vector? Well, doesn't it make sense if we're trying to find the angle with the positive z-axis that we just use 0, 0, 1? You could use 0, 0, 28 if you want, or whatever, but you only 0, 0, 1 will do. And then down here, we're going to need the magnitude of the 2, 0, root 5 vector times the magnitude of the 0, 0, 1 vector. Of course, that magnitude is 1, but I'm just trying to illustrate that point. And so this actually ends up being cosine inverse of root 5 over 3. Okay, whatever angle that is. Finally, we spin all the way around in terms of what theta angle, so theta will be between 0 and 2 pi. Okay, so that took some work to do, but we've set up, I think, or at least wrote that information down. We'll set up, we did the hard work for setting up the integral. Now we actually have a bit more work to do for the part that's below. Again, this is the part that's shaped like this. It's like it was a cylinder before, but then in here, there's a cone of stuff that has been gutted out. So it's like the only part so this cone has been removed. That part's empty, but then there's this part. And I should fill in front of the cone, but I don't know if I shade that, if that's helpful in terms of drawing. This part over here for sure, there's nothing getting in the way, and we're saying we want all that stuff. So what about the values of rho? Well, you'll notice that there are points that are near the origin. So it makes sense to do this. But what about the upper value? Now this is going to get tricky, okay? The thing is, the largest that the value of rho can be is going to depend on, well, we're going to write this actually just in terms of punchline here. It's going to be written in terms of phi. And you can see this from the picture, because maybe I'll use a color here, that when you look at the angle phi, which, at the smallest for the shaded region is there, but it could be here, it could be there. And you'll notice that each time the value of rho, the largest value of rho, is different for different values of phi. In fact, if phi is 90 degrees exactly, then the value of rho we can see from the picture is going to have to be 2. But if you look at this angle right over here, you actually spend a lot more time in the shaded region until you finally leave, right? So we need to figure out what that looks like. And so, how do we do this in terms of phi? We just draw a sort of a flattened version of this picture by doing this. Let's say here's the origin. Say this is the positive z-axis. Okay, we've got this value rho that we're trying to find. We have the angle phi is technically here, but by drawing a parallel copy of the z-axis here, or your line segment that's parallel, we're going to have this, and then this distance is again z. Yeah. Now this distance this way, it's from here to here. Sorry, maybe do it back in this picture. It's from there, the tip, to there. So for the cylinder, there's a point at the bottom. It happens to be the origin, and then there's this point here, which is like 0 to 0, for instance. So this distance here, it's actually no matter where you are located, it's always x squared plus y squared. In other words, it's equal to 4. Or sorry, it's where x squared plus y squared equals 4. So that distance here is actually going to always be 2, right? Because from the origin, just in the xy plane, to any of any of the points that define this cylinder, every time the distance each of these line segments is 2. So that's, yeah, this way there's a distance of 2. The point is that we can now look at this picture and say, based on where phi is, that sine of phi is equal to, let's see, opposite of 2 over hypotenuse of rho, 2 over rho. And so then, multiplying both sides by rho, we get that rho sine phi is equal to 2, and then we're trying to solve for rho. Rho equals 2 over sine phi. Okay. We could, if we'd like to, just write this as rho is equal to 2 cosecant phi. Right. So in terms of a bound, that's as far away as rho gets. So you can even visually see the smaller that this angle is, then the bigger that rho is going to have to get. And that's reflected by the largest possible rho value for a given value of phi. The largest value of rho is 2 times cosecant phi. So let's summarize here that we've got 0 is less than or equal to rho is less than or equal to 2 cosecant phi. And then how about a bound on the phi angle? Well, we're actually, from this shape here, let's see if I can get, probably can't. But like we start here, and then we fan out this way. So the starting angle was actually the last integral stopping angle. So we've got here cosine inverse of root 5 over 3. And where does it stop? So maybe I'll draw in a new color on top of this in the hopes that it'll be visible. So there's our starting angle. And then we keep fanning out, and bigger values of phi are fine until we get to right on the xy plane because of this z equals 0 being a place to stop. So we end up stopping at phi equals pi over 2. And then values of theta, well, we do go all the way around in this sense. I use a new color, hopefully it's visible in that way. So theta is going to go from 0 to 2 pi. It turns out then, so due to the kind of odd shape that we have, we actually have to set up an integral here and an integral there and then add these up. So we've got an integral of 1 rho squared sine phi d rho d phi d theta. And then for this ice cream part above, rho from 0 to 3, phi from 0 to cosine inverse of root 5 over 3, and then theta from 0 to 2 pi, plus another triple integral, 1 rho squared sine phi d rho d phi d theta. And then rho now goes from 0 to 2 cosecant phi. And then phi goes from cosine inverse of root 5 over 3 to pi over 2. And then finally theta goes from 0 to 2 pi. Oh, that was quite a lot of work, huh? So, what I'd like to do is ask, based on this question, the following interactive question. So why couldn't we just simply, do this all as one triple integral? Or question, why did we need a sum of triple integrals in spherical coordinates?